Hello everyone, I am Soumyakanti Behera, a third year Electronics and Communication Engineering undergraduate student at IIT Bhubaneswar. And in this video, I am going to talk about the first experiment of our Digital Signal Processing Laboratory course. So in this experiment, our aim is to write an Arduino program for studying the performance of moving average filter and first order derivative filter. So the three filters we'll be discussing about in this video: a moving average filter, derivative filter, first order difference, and derivative filter, 3-point central difference. Now, the moving average filter. It is a low pass finite impulse response filter commonly used for smoothing an array of sample data or signal. It takes L samples of input at a time and takes the average of those L samples to produce a single output. In simpler words, it takes the average of L previous inputs to generate the output. The equation of the filter is as follows: y of n equal to 1 by L summation k equal to 0 to L minus 1 x of n minus k. As the length of the filter increases, the smoothness of the frequency increases, whereas the sharp modulations in the data are made increasingly blunt. But at the same time, its cutoff frequency decreases, which means, like, if we go on increasing the value of L, after a certain point of time, the filter may remove useful information from the signal as well. Now we have the impulse response h of z of L point moving average filter. uh, this is the transfer function of the L point moving average filter, which we obtain by applying z transform on the equation we had on previous slide. So h of z here equals to 1 by L summation k equal to 0 to L minus 1 z raised to minus k. Now we observe the performance of this filter by doing the frequency analysis of the impulse response h of z obtained above in MATLAB software. So here we can see the above graph shows the magnitude response of h of z, whereas the below one shows the phase response. Now coming to the derivative filter. The derivative filter is a periodic finite impulse response filter or FIR filter which provides a quantitative measurement of the rate of change in pixel brightness information present in a digital image. So basically it functions as a high pass filter which is used to allow high slope portions of a signal. There are two types of derivative filters. The first one is first order difference filter. It is a causal and LTI filter whose output depends on the current input and the previous input. It is basically used to highlight high slope regions in a signal. And the second one is 3-point central difference filter. It is also a causal and LTI filter which considers two input sample about a input sample to produce the output, which means it considers the penultimate input to produce the output. Therefore, it is quite more accurate than the first order difference filter. So now we have the equations of the two derivative filters we discussed in the previous slide. The first order difference filter, as we said, that the output depends on the current input and the previous input. So we have y of n equal to x of n minus x of n minus 1. In case of the 3-point central difference filter, we had mentioned that the output depends on the current input and the penultimate input. So we have y of n equal to x of n minus x of n minus 2. Now we apply Z transform to the above two equations and we obtain the frequency response or the transfer functions of these two. So in case of first order difference filter, we have h of z equal to 1 minus z raised to minus 1. Whereas in case of 3-point central difference filter, we have h of z equal to 1 minus z raised to minus 2. Now we have the magnitude and phase response. So the blue line here shows the first order difference filter and orange line shows the three-point central difference filter. Now coming to the experiment questions given to us in lab 1. In the first question, we have to choose a filter to smooth out high frequency noise present in the signal. So in order to do this, we use L point moving average filter with L equal to 8. So we write Arduino code for the same. In the first few lines of the Arduino code, we initialize the input mm, x and the output y, and n equal to 1000, where n is the total length is the total length of the input signal, and int l equal to 8, where l is the length or number of blocks of the moving average filter. Now, as every Arduino code, our code has two parts: void setup and void loop. In void setup, we initialize the baud rate to be 9600, and in void loop, we write the block of codes that we want to repeat again and again in order to get the output. So here we have nested for loops. The first for loop here navigates through all the components of the input signal for int I equal to 0 to I less than n, which means it takes all the components of the input from I equal to 0 to I equal to n. And the second for loop here calculates the moving average for each and every component. And after that, we use the serial print function to display the outputs. Now we'll have a look at the outputs. Here, the blue one shows the original signal that we fed into the moving average filter. The red graph here shows the output of the moving average filter, which is the smoothened signal we were supposed to obtain in the question. So that's an end to question number A. And now we coming to question number B. We have to choose a filter to emphasize high slope portions in a signal. We know that the derivative filter could be used for emphasizing the high portions of a given signal. As the given signal is observed to be PPG, so we could highlight the local maxima of the same. Here we are going to use both the discussed derivative filters. So in this question, one thing that we have to do is before passing the input signal through any difference filter, we have to smoothen out the signal. Because if the signal is not smoothened out, then all the noise portions will have high slopes and they will be detected in the difference filters. So we pass the signal through a moving average filter and then we pass it through both the derivative filters we discussed. So the first few lines of code is similar to the previous one. We initialize the input x, the outputs ya, yb, and y, and n equal to 1000, where n is the length of the signal, and l equal to 8, where l is the length of the average moving average filter, or the number of blocks in the moving average filter. So here in void loop, firstly we write the code for moving average filter. It is exactly same as the previous code. We have nested for loops. The first for loop navigating through all the elements of the input, and the second for loop calculating the moving average. After that, we pass the output of the moving average filter through the first order difference filter. Here we write a for loop, which navigates from I equal to 1 to I equal to from I less than n, and we have ya of I equal to y of I minus y of I minus 1. This is the equation for the first order difference filter. Now we have the second for loop for the 3-point central difference filter. Here we write yb of I equal to y of I minus y of I minus 2. Now as we have got the outputs, we use the serial print function to display the outputs. So here's the output of question number 2. The, the blue graph here shows the smoothened PPG signal, which is the output of the moving average filter. The red graph shows the first order difference filter's output, and the green one shows the output of the 3-point central difference filter. From the red and blue graph, we can conclude that the 3-point central difference filter detects the high slope regions more accurately than the first order difference filter. Now coming to part C of our experiment, We have to design a moving average filter with L equal to 8 to extract baseline drift component from a signal. So baseline drift component is basically the DC component that gets mixed with the PPG signal. So in order to solve this problem, we'll follow a few steps. In the first step, the given signal will be fed to a moving average filter to remove the high frequency noise and to smoothen the signal. And after that, we'll feed the output of the first moving average filter to a second moving average filter with a considerably large value of L. Here we have taken L equal to 800 for the second moving average filter. And finally, the obtained baseline drift, which is the output of the previous moving average filter, we subtract the baseline drift from the smoothened signal to obtain the original PPG signal. Coming to the Arduino code, we have the first few lines of the code similar to the previous two codes. We initialize the input, we initialize the outputs y and z. We initialize n equal to 1000 where n is the length of the input signal, L equal to 8 where L is the length of the first moving average filter, and m equal to 800 where m is the length of second moving average filter. So in while loop, we write we write nested for loops for the first moving average filter, and here we have the the code similar to the codes of the previous two questions. And after that, we write the code for the second moving average filter where the length of the filter is 800. So the second moving average filter gives the output which is the baseline signal. So in the end, we subtract the baseline signal from the output of first moving average filter to get the original PPG signal. And as in previous questions, we are using the serial print function to display the outputs. The blue graph here shows the input PPG signal, and the green graph shows the extracted baseline drift of the PPG signal, which is also the output of the second moving average filter. The red one is the corrected PPG signal or the smoothened signal, which is the output of the moving average filter with L equal to 8. And now coming to the part D and the last part of our lab experiment. We have to find the output of signal processing system which performs first order derivative filter and then performs moving average filter with n equal to 8. In this experiment, we just have to we just have to write the first order derivative filter code and followed by the moving average filter code. So coming to the Arduino code, we initialize the input, the two outputs y and z. We initialize L equal to 8 where L is the length of the moving average filter, and n equal to 1000 where n is the length of the input signal. So in void loop, uh, we write a for loop which in order to calculate the first order difference. So basically, y equal to y of I equal to x of I minus x of I minus 1 is the equation of first order derivative filter. And the for loop navigates from I equal to 1 to I equal to 1000. And after that, we write two nested for loops for the moving average filter with L equal to 8. And similar to all the previous three codes, here the first for loop navigates through the different components of the signal, and the second for loop calculates the moving average. And in the end, we again use the serial print function to display the outputs. So here we have the blue graph, which is the original PPG signal recorded, and the red one shows the output of the first order difference filter from the original PPG signal. And finally, the green graph shows the smoothened output of the first order derivative filter, which is the output of the moving average filter. So that's all for today. Thank you.